Hello friends, in the previous class we have learned about the problems relating to the working stress method and also how do we calculate the depth of neutral axis and the stresses in the concrete, as well as how do we calculate the moment of resistance. So these things we have studied in the previous class, and in the today's class we will be discussing about some design type of problems relating to the working stress method. So let us start with the problem number 3, and the problem says a RCC beam of span 5 meter, that is the effective span we are provided here, carries a UDL of 20 kilonewton per meter. So that we are having the UDL uniformly distributed load of 20 kilonewton per meter, and we are to design the depth and the area of the steel if the beam is 250 mm wide. So we are also provided here with the width of the beam. We are to use the M20 concrete and Fe415 steel. So we will be using the M20 concrete and Fe415 steel for the design. So let us start with the given what is provided in the question. So what we are going to write here is the depth of the beam, that is 250 mm. As we are using the Fe415 steel, so the value of the Fy, that is the yield strength, would be equals to 415 Newton per mm square. And as we are to use the M20 concrete, the value of the FCK, that is the characteristic strength of the concrete, would be equal to 20 Newton per mm square. Let us draw a diagram here of the simply supported beam. Okay, so this would be equal to 5 meter that we are already provided in the question, that is the effective span. And at the top there is uniformly distributed load of 20 kilonewton per meter. These are all mentioned in the question. So let us start with the problem. So first of all, what I am going to do is I am going to calculate the value of the CBC, which is nothing but the permissible compressive stress of the concrete in bending. So that is equal to FCK divided by the value of factor of safety. So the value of FCK is 20 and the value of the factor of safety for the concrete we will be using it as 3. So on calculating this, what we can obtain is 6.67. Now what we have to do is we have to refer to IS 456 2000. So let us go there. As you can see, I have referred to IS 456 2000 and the page number is 81. So at the top of the page we can see the table number 21 and the topic is permissible stresses in the concrete. So for this, what we can see is we have taken the value of the sigma CBC as 7, and for the corresponding 7 the grade of the concrete is M20 that we have to use in this design process. Okay, moving on, we are also finding the value of the sigma ST, which is nothing but the value of Fy divided by the factor of safety. So the value of Fy that we know is 415 divided by the factor of safety. For the steel we will be taking it as 1.78. On calculating, what we can find here is 233.146 Newton per mm square. So we will be again referring to IS 456 2000 and page number 82. So this is page number 82 of IS 456 2000, and at the top of the page we can see the table number 22 deals with the permissible stresses in steel reinforcement, and what we have found is the value of the sigma ST, that is 230 Newton per mm square. So this is for the Fe415 steel. Now let us find the value of the maximum bending moment, and we know for the simply supported beam the value of the maximum bending moment is WL square whole divided by 8. The value of the W that we are provided is 20 times of the length of the span, 20 into 5 square divided by 8, that should be equals to 62.5 kilonewton per meter. So for the balanced case, what we can do here is we can assume the maximum bending moment should be equals to the moment of resistance and the tensile force should be equals to the compressive force. So for the balanced case, what we can write is NC, that is equals to N1 times of D, that we have already discussed in the previous question, where N1 means M divided by M plus R, and R means T divided by C, which is nothing but the value of the sigma ST divided by the value of sigma CBC, which we have already found, that is 230 divided by 7, that should be equals to 32.85. Now we are going to find the value of N1. For that we will be needing the value of the modular ratio. So what we know, the value of modular ratio is nothing but 280 divided by 3 times of sigma CBC. So that should be equals to 280 divided by 3 times of 7, and the result would be 13.33. So what we can write here is 13.33 whole divided by 13.33 plus the value of R that we have found earlier, 32.85, and on solving this, the value of N1 should be equals to 0.288. So the value of NC, what we can write here is 0.288 times the value of effective depth. We are still to find the value of the D. So moving on, what we can write here is, for the balanced case, the moment of resistance should be equals to the maximum bending moment. And for this what we can write is half of B and C times effective depth minus 1/3 of depth of the neutral axis should be equals to the maximum bending moment. And the value of the maximum bending moment that we have found earlier was 62.5 kilonewton meter. So referring to that, the value of the maximum bending moment we can write as 62.5. Now what I am going to do here is I am going to multiply it by 10 to the power 6. You might feel like, why I have multiplied it by 10 to the power 6, but because the value of the B that we will be using here is 250, that is in mm, and the value of the D that we are to obtain will be also in mm, so that I have multiplied it by 10 to the power 6 to reduce it to Newton per mm. So what I can write here is 1 by 2 times 250 times the depth of the neutral axis. What we can write is 0.288 times of D, because this should be equals to the critical depth of the neutral axis, times the value of the C, that is nothing but the sigma CBC. This means sigma CBC times the depth of effective depth minus 1/3 of 0.288 times of D again, and that should be equals to 62.5 into 10 to the power 6. And on solving this, the value of D, we can find it as 523.78 mm. So rounding off, I will be taking the effective depth as 550 mm for the convenience. So now what I am going to do is I am going to equate the value of tensile force to the value of compressive force. You know, the value of tensile force would be equals to sigma ST T times of AST, and that should be equals to half of B and C. Here T means nothing but sigma ST and C means nothing but sigma CBC. Don't get confused here. So that should be equals to 230 times of AST, that should be equals to half of 250 times 0.288 into 550 that we have found earlier, times of 7, and on solving this, the value of AST should be equals to 602.608 mm square. So for this I'll be adopting 16 mm die bar. Now the area of the reinforcement, that is individual area, should be equals to pi d square by 4. So what I can write here is pi by 4 into 16 square, and that should be equals to 201.061 mm square. So the number of bars that we have to provide throughout the beam section is 602.608. That is the value of AST. This is the value of AST, and divided by 201.061, and that should be equals to 2.997. So rounding off, we will be providing 3 reinforcement each of 16 mm diameter. So what we can write here is provide 3 16 mm dia bar. Now let us draw this beam section. This should be our neutral axis. Here I will provide the reinforcement. This is our center of reinforcement. And all three are 16 mm diameter. And the width of the beam that we are provided in the question was 250 mm. And here the depth, that is the effective depth, should be equals to 550 mm, and throughout depth this should be equals to 600 mm. So this is all for today. We will be dealing with some more questions in the next video. Thank you.